By the way, if you're curious why we always start the video 1 minute early, which is annoying because you've got a minute of just me staring at the computer if you open a video, is just in case the recording fails, we've got 1 minute to fix it. Usually that's just enough time. It looks like we can officially start. Welcome back, everyone. So I have all these announcements here that are drawn on just so I don't forget to mention them. Big announcement is we have our first assignment. Assignment one is due today. And there's lots of ways to hand this in, like I mentioned. All depends on how you're working on this assignment and how you like your assignment back. A lot of people have sent in their assignment already digitally. I appreciate Word documents, PDF documents. Those are pretty easy to open. But if you're working on your assignment in a more traditional way, paper and pencil, that's always completely fine. You can take a scan of your work or cell phone pictures of your work, send it into the email or hand it in down here at the start of class. Again, all kind of up to you, whichever works best for your workflow. And if you're doing it, say, as a more traditional class where you're just writing down your results on a notebook paper, or maybe printing out the assignment and filling in the blanks in there, you might have some issues with sending in your graphics, but you can just email me what the graphics are, and that will always just qualify. Just say, for example, one, something like that, so I know which is which. But honestly, when you produce a histogram or a bar plot, anything like that, you should have enough description on the vertical axis, horizontal axis for it to be determined which problem it belongs to anyways. So usually that's not a big issue. But any questions at all, folks, on getting the assignment turned in, anything like along those lines? Okay. And like I mentioned, if you email me your assignment, that means when I grade it over the weekend, I'll just be emailing it directly back to you. Watch out if you're using an external email address. Not that it's disallowed, but it just means you have to be aware to watch that email address for when your graded assignment gets returned to it. And if you turn in a more traditional copy, say a hard copy down here at the start or end of class, I'll just get that back to you when I see you next on Tuesday. So pretty much this is how all the assignments are going to work. We have assignment number 2. It's due February 6th. We pretty much finished these notes, but we didn't get to the last table. And my pattern on this is I feel like we should finalize everything on this document before assignment 2 is officially assigned. So I pushed the due date from a week away from today. We'll definitely finish chapter 2 today. And chapter 11, we could potentially finish this today. We're not going to try to rush and make that happen. But another thing I don't like is I don't like 2 assignments to be due on the same day. So even if we finish chapter 11 today, I have the due date pushed, so it's not too much coming in at one moment. Well, aside from that, another reminder, we have our first exam. We're not up to the third yet. Our first upcoming exam is just about not quite 2 weeks away. It's going to be on Tuesday, February 11th. So Tuesday of this week here. And I'll be working over this weekend on filling out information on review documents, exact coverage, that kind of stuff. I think that fills it out, all the announcements. Any questions at all, folks, before we get started? Okay, well, we're pretty much done with chapter 2, but the last table that we need to come back to was mainly just to help out with some of the homework and just determining which statistics we should use to measure the center spread amongst these 3 different situations. We are very happy when our data is at least roughly symmetric, but we grow concerned when we know it's clearly skewed, either direction, left or right, because we have to change their type of statistics, which has a big effect of changing the inferential statistical procedure that we'd have to use as well. So let's draw out a couple of these histograms just for more practice identifying these by eye because it's a purely qualitative analysis. Starting with the one that's at least roughly symmetric, we would have a main peak where the data aggregates somewhere towards the center, maybe not dead on exact. If we start drawing off our distribution like this as a histogram, we have some great symmetry going on. At this stage, we might say that this is highly symmetric data. but symmetry starts to fall off as soon as we have maybe something like this. That is a little bit concerning. It could potentially be an outlier. We would maybe want to check using the 1.5 IQR rule of thumb, implemented through the box plot. Let's just mention that as a comment. A box plot, if you're checking for an outlier, is really effective. It will use the 1.5 IQR, let me try again, IQR rule to test for outliers, like what this one seems to be. But again, this would be at least roughly symmetric data. And we mentioned if our data is at least roughly symmetric, best way to measure the center will be X bar, the sample mean. Best way to measure the spread would be S, and this is the sample. Standard, I'll abbreviate to STD, deviation. I'll abbreviate to just DEV. So those are the statistics we'll use for center and spread. It's the statistics we prefer to use as many times as we can get away with it. Unless our data is beyond roughly symmetric, it becomes skewed in either direction, or has too many influential outliers. Other big problems could cause issues over here. Then finally over here, it's always interesting to compare the things that measure the center. If our data is at least roughly symmetric, what we would say is the sample mean X bar would be approximately equal to the sample median M. The 50th percentile is about where the sample mean would be. So again, this is more just synthesizing some of the discussions we had earlier in this chapter too. Any questions at all with row 1 of this table? Okay, then here's when the data just really goes bad. Let's make something that's very skewed left. If we have data that's looking like this, for example, that data is fantastic. But if it starts to do something more along these lines, now we have something that is just absolutely skewed to the left. That's kind of a weird, shoddy by hand drawing. So use your imagination. Imagine they're perfectly equal with rectangles there. But now we have something clearly skewed to the left because of the way the data is trailing off in this left side right here. This time, we wouldn't want to measure the center using X bar. Anyone recall what we should use in this situation? Yeah, go ahead.
Shouldn't the center be the median?
Absolutely. No matter how skewed it goes to the left, the median is going to be robust against that direction of skewing. And so it'll always be the best way to measure the center. In fact, we had kind of an informal experiment in class when we went up to this problem. We calculated X bar using our studio, but before we did that, we just asked the class, where does it look like the center is? And I believe, maybe I pointed there, but I believe as a class we said maybe around here. And yeah, it turns out that we think of this as being the center. The median is actually right around here, but the sample mean got pulled off into the other direction. No one would say the center is right here for the data. So in that sense, the sample mean fails when our data is skewed enough. So coming back down here, that's why we're going to use the median to represent the center, as you said. M, the sample, median, which is again the 50th. Can't quite fit that in there. Let me just see if I can get this in on the margin, just as a reminder. It's not a margin, but we'll call it a margin anyways. We'll just recall that M is the 50th percentile, which means it's a number that cuts the data set literally in half. There'll be half, 50% of observations below, 50% above. Now, if we use the median to represent the center of the data, our choice is kind of fixed for the spread. Anyone recall what has to go along with the median now?
The
Close. It would be called
interquartile.
yes, good call, the interquartile range. We would be using quartile 1, the 25th percentile, quartile 3, the 75th percentile to do that measurement. So IQR, which is the interquartile range should be used. And this is defined by IQR equals quartile 3 minus quartile 1. Our studio can do that computation for us, but just writing it down reminds us what it is. The IQR is the distance that contains the central 50% of all observations. And the wider that distance is, the more spread out your data is. So in that way, IQR measures the spread. But over here in this column, X bar compared to M is not this picture. They're not approximately equal any longer. When we compare X bar to M, what would you put in the middle? Is this a less than, or should we put in a greater than?
Greater than?
It turns out it wouldn't be greater than on this one. And the reason is only because of the left skew directionality on this. The median itself is probably, I'd say somewhere maybe about here for the median. But because it's skewed to the left, the sample mean X bar gets pulled somewhere out here. The more skewed it is, the further to the left it goes. For these data, we had numerical values, we probably see that it's way out there. So we would relate the sample mean with the median by a less than in this picture, which kind of makes sense in a way, less than for left, and would use greater than for right. Makes sense in a certain sense, I guess, maybe not a perfect way to think about it. That's what happens when our data is clearly left skewed. We change our statistics, and the reason is really because of this. Our center is no longer center, it's off-centered, pulled to the left now. This table is basically the reflection of this, but we might as well finish out the last row. Any last questions, folks, on either of those rows? Okay, so let's make something that is just violently right skewed for this one, just for the fun of it. Something that's outrageously right skewed could be like this. Almost all the data is right there. Then we have some observations that are falling off in this kind of way. Maybe some absolutely terrible influential outliers. This could be our clearly skewed right data. The right skew on here is due to this, as well as these definitely outliers here that we see on the far end. Here, we wouldn't necessarily need a rule of thumb to say they're outliers when they're this far away from the main grouping of the data over here. So we have something that's violently right skewed. This would be something that could correspond to, say, incomes. You would have, say, in the state of Idaho, most people here. Then you have the very, very filthy rich people that are skewing it violently to the right-hand side. So incomes often fall into a picture that looks about like this. But like we said before, we are going to measure this the same. It doesn't matter if it's skewed left or right. We now need the median for this level of skew for the center, IQR for the range. And due to the right skew, this directionality changes. The sample mean is pulled to the right, so we use a greater than due to that right skew. For just another quick addition here, our median is probably somewhere in this location, but these outliers are so influential that, X bar could be really clear out here, not even centered above any data at all in the histogram due to these observations. So because of that, once again, X bar falls on its face, and we resort to other statistics, which are more challenging to work with, but it's what we have. When I finally finalized chapter 2, and some of these problems, especially concept questions that could come up on exam 1, pretty much you're going to see these distributions be asked which statistics represents the center, which statistic represents the spread, based off the amount of symmetry or skew that you see. That's a challenging question because I'm not asking you to calculate X bar nor S. That's a RStudio problem. I wouldn't ask you to do that on the exam. You're just saying which statistic you have to use, like we did here. So watch out for those kinds of questions. They're not intended to be tricky, but they have that side effect sometimes. Well, let's save this up. Now we're skipping over to chapter 11. Our objective in this class is statistical methods, like the title says. Getting into the normal distributions gets us very close to those methods. So let's see where we're at so far. I mentioned here with the normal distributions that, well, we can model a lot of interesting data by a normal distribution. A lot of things seem to follow it, say the length of a fish in a particular population of a certain kind of fish, or heights of people in a country. If we put all those types of quantitative data into a histogram, oftentimes it is normally distributed. But I should back off. It's not that they're exactly normally distributed. The normal distribution is just a mathematical thing. Oh, sorry, I missed a chat. Hay says, do we download the ARM syntax for this chapter 11? Actually, I don't think I have any specific R syntax for chapter 11 or data sets. We'll be using RStudio kind of like a calculator, like a TID4, finding areas and values on the x-axis. So nothing too specific from chapter 11. Well, other questions, folks, before we get started here? Okay, so like we mentioned, a lot of things seem to be normally distributed, but the most honest way to say that is we can use the normal distribution model, that's the wrong notes, in a lot of situations. So let me go back to chapter 11. So here's the problem with the normal distribution. It's that function. And there's no reason to believe that the heights of people in the country are obeying this exactly. It's just a model that is approximately correct. If we tune the parameters better and better, its accuracy could improve. But the reason we need the normal distribution, again, is not because we can model it well to data. It's more about what's going to happen in the next chapter when we get into the concept of sampling distributions. Well, let's get started with this. We'll say here, if we have a continuous random variable, x could be, again, heights of people in a country, x could be distances from a starting point, anything that's quantitative. We'll say it's normally distributed with a mean mu, standard deviation sigma. But you might recall from chapter 1, mu and sigma are population parameters. Let's say it here, mu and sigma are population parameters. This means in a normal statistical problem, these quantities are true unknowns. The whole goal of inferential statistics is to estimate them. But chapter 11 goes a little bit differently. In chapter 11, we'll have data that we're trying to model with a normal distribution. So what we do in chapter 11 is make a best guess at both mu and sigma to try to take a curve like this one and fit it over histograms like these to try to model the data. It's going to fail on this one, but do an okay job on this one. But again, we don't expect the nerve cells in the intestinal wall of a pony to follow this exactly. This is just our best way to hack a curve onto the histogram that seems to express the data well. So the performance of this model is often suspect, but sometimes it's the best thing we have. Well, if we were to try to plot this thing, here's what it looks like. Again, it's an interesting mathematical function, but it's called a density curve. Other textbooks might call this a probability density curve, which is shorthanded into PDF. Let's say that right here, just for the sake of if you have looked at these kind of ideas before in another statistics class, here's how it connects. The density curve can be also called a probability density curve, and that's shorthanded to PDF oftentimes. The probability density curve has to satisfy a couple operations. The first one is that the curve f of x has to be greater than or equal to 0 for all x. We would say all x in the sample space, but here the sample space in the normal distribution is automatically all real numbers, the entire real number line from negative infinity to positive infinity. So it's not as useful concept if we're just looking at normal distributions to even bring up the sample space, just the whole real number line. So to have a probability density curve, we require non-negativity. So the curve has to be greater than or equal to 0 for all x's. And property 2 is the weird one. Again, this class is a little bit strange. They programmed in a requirement of calculus 1 in this class, which is odd because we don't do a lot of integration. And there is no prerequisite for statistics in the first place for us to really go far into a calculus direction. But statistical methods still need some ideas from calculus. Perhaps that's why it's in the prerequisites. The idea is we need to be able to integrate from negative infinity to positive infinity. That's a calculus 2 concept. Again, the prerequisites of this class are just a little bit wonky. So if you haven't taken calculus 2, you're still just fine. If you haven't taken calculus 1, but you know some ideas from calculus, you're just fine as well. So we integrate from negative infinity to positive infinity. That's a type 2 improper integral for the calculus 2 folks. It just means the entire real number line is the domain of integration. We're integrating the function f of x. We say dx just to say the variable of integration. And this must be 1 exactly. And it turns out that's true for this curve, which is pretty surprising. Its domain is all real numbers. So this arrow goes to the left forever. This arrow goes to the right forever. It's never even touching the x-axis. For that curve f, we really have that property. It's strictly greater than 0 always, because the exponential here can never take a value of 0 whatsoever. In general, though, it just has to be greater than or equal to 0, so I'll leave that in. So this curve has an extent infinitely to the left, infinitely to the right. It's never hitting the x-axis, yet the area between this curve and the x-axis is exactly 1. It's not infinite. That's already a pretty strange concept. But that's our introduction to the normal distribution so far. Any questions at the moment? Okay, this formula here, it's more for the sake of completeness, because if you draw a curve, the natural curiosity is, what is the function or formula that generated it? And this notation here we'll actually use quite a bit. When we say x is distributed normally with a mean mu, standard deviation sigma, we can say this in probabilistic terms in this way. X is distributed as, is what the tilde is saying. N means it's distributed normally. And we say it has a mean mu, standard deviation sigma. So our author uses this notation a lot. He asks for it in problems. When this comes up, he'll often say, what is the probability distribution of x? And this is what's being expected for that answer. But you know what you can always do if you're not a big fan of symbols like this is, you can always just read it out and say, x is distributed as normally with mean mu, whatever the value is, and sigma, whatever that value is there. Think of this as just a very, very compact way to say it. We'll study this a lot to make it familiar. So that's the notation, definitions, some graphics of what's going on in this section. What we'll be doing is looking at when we can use a normal distribution, when we should avoid it, and do a couple problems where we're modeling data with this distribution. Well, any questions so far, folks? Okay, now, again, another thing to bring up here is this is a tough curve. Doing an integral like this is pretty tough as well. These areas are going to turn into probabilities, so we need to calculate these areas. But to do this integral, this is a tough one. In fact, it can use calculus 3 techniques where you make a change of variables, a whole bunch of crazy thing happens. But RStudio doesn't care. Think back in calculus 1, when you're trying to do a really hard integral, you can use the midpoint rule, the left-hand rule, Simpson's rule, all those kinds of things to approximate. RStudio has all that ready to go. It is extremely fast at doing numerical approximations for this curve right here. And then says, is the antiderivative of f prime of x. Oh, that's a good question, Ben. That's a hard thing to get on here. This is not an easy antiderivative in any sense of the word, but this one is considered an improper integral. It's a type of indefinite, excuse me, it's a type of definite integral where we put a limit for the upper limit and the lower limit that goes off to infinity. But because it's a type of definite integral, it's evaluating to a constant. Whereas if you went like this, we would have to put a whole function right here to say what the antiderivative is. Again, not a very easy antiderivative to come up with. Other questions about that so far? Does that help with that question there, Ben? Yeah, absolutely. Any other questions at the moment with this crazy looking model? Okay, well, down in the notes, here's where we're going to start practicing with it. I also want to mention maybe another interesting thing is that we're going to be using RStudio to do our normal probability computations. But if you've just gotten a really good habit of doing the same computations through a calculator like the TID4, that's totally fine in this class. I'm not going to ask you to do these computations in an exam setting. It's going to be more about the interpretations of the computations when you go to do these on the exam. So pick your favorite computing environment. I'll be using RStudio. It is pretty fast, but you don't have to change your methods if you don't want to. You'll be totally fine. So here's some of the comments that we met before. Domain is all real numbers. Never intersects the x-axis. That's impressive. Yet the area is exactly 1. And the next concept we have to connect here is how the areas under this curve will correspond to probabilities. So we need some context next. And let's see here. Yeah, that's what's going on in this problem here, example 1. So we have a population of herring fish. It's this right here. If you go over to Microsoft, if you want a good visual here, click on, let's see, search. This is a pretty good strategy. Oh, it doesn't work anymore. It was a pretty good strategy until Microsoft Word took it out. I guess they're trying to pump Bing or something like that. But it's sometimes a good idea to search these things. I'm kind of embarrassed it didn't work today. I don't want to use Bing. Let's throw that away. Let's take this and just use a ordinary Google search. My comment was, sometimes if you're doing a statistical problem and if you're not aware what these even look like, it's actually kind of a harder problem. The more familiar you are with the context, the easier it is to absorb these kinds of things. So let's open up a browser and do just that. So looks like this is the type of fish that we're dealing with. We want to try to model these using a normal distribution, but we have to know what we're modeling. Could it be the mass, the length, something like that? But we've got a visual at least. That was the whole point of opening up this browser. Kind of a misadventure in Microsoft Word. So we're dealing with these fish. We're told that they have lengths of individual fish, which follow a normal distribution. That's pretty good information right here. Again, what they're saying really is we believe that the population of these fish is well modeled by a right specific normal curve. We just have to pick the parameters. We're not saying it follows that exactly. This part is us picking the parameters. The mean length is 54 millimeters. In our language, our symbols, we would say mu because we're describing a population. This is a true unknown. 54 millimeters is just our best guess of that value. So mu is 54.0 millimeters. Population standard deviation. Our symbol for standard deviation, when we say it's a population's deviation, is sigma. It's another parameter again, because we're describing the population, not the sample. And we don't know the value of sigma, but we're saying it's dead on equal to 4.5 millimeters, only because we're trying to model the data, no other reason. We're not saying we know this as fact. So anytime we read a statistical problem, this is a good idea to just kind of troll through here, see what information you can highlight as important, see what information you can write down in our notation, abstracting it away from the way they say in their problem, Finally, they say X is a random variable, and this one is going to denote the length of the randomly selected fish in that population. So X measures the lengths. That makes sense. They said the lengths follow a normal distribution with those parameters. So that's what we're modeling. And in a lot of homework assignments, this has the potential to be the most confusing question ever. I get the most questions about this one, it turns out. We get used to it when we see this coming up over and over. But let's be careful with this. When it says, what is the probability distribution of X? We just want to know, how are you going to model X, the lengths of all these fish, when you select a random one from the population? From the information above, we would say X. A little tilde here deserves an explanation. Read the tilde as is distributed as. So that's all our tilde is trying to convey. We said it's distributed as a normal distribution. In their words, they said it follows a normal distribution, but this is what they're entailing. So we'll just put down n. So n takes the role of the normal distribution now. The way you define the normal distribution is through two parameters. The first parameter we pass to it is the mean, 54.0. So in other words, just as an extra symbol for a reminder, mu always would go right here. This is where it gets a little exciting though. Depending on how much statistics and probability you've taken, there's disagreements on what should go there. Some people put the variance, which means you would square this number and drop it in there. That's usually if you're in a probability context. If you do put the variance in there, I'm totally fine with that. I'll tell you squared something and that's what it was, so you don't have to change your notations. But in our book, we put in the standard deviation. So 4.5 is what would go into that location. So this is the value for sigma, just written lightly as a reminder. That's what goes into that position. And this is all you have to do to answer that question entirely. Any questions with this answer here? Okay, I like this way of writing things down because, well, a couple reasons. It's compact. You're not going to use as much oxygen to express what you're saying here. Second reason, it's all over the place in the reading of the book that we're using, so it makes good sense to use it in our notes as well. But again, if you format things in a different way and you're saying the same exact thing, you can never possibly lose credit in this class if you're just as correct. Let's call this option one. Option one is to use really compact notation, and you've said what the probability distribution is. For folks who are not as big a fan of notation like that, option two, equally correct for full credit, would just be to say X is normally distributed with, you could say mean mu, but that's honestly just super redundant. When you're looking at mu, we already know it's a population mean. So I would just say with mu is 54.0 millimeters. That's not an M at all. Let me try again. And sigma equals 4.5 millimeters. I like this route too because, I mean, it's just ordinary speech. And sometimes if you're trying to write down results that other people are going to understand, this is better. If you're trying to write down results that you're just doing as compactly as possible, following along the book, and you're not worried about anyone else reading it, this is better. So just pick out what makes most sense and you're going to be totally fine. But we did it. This is probably the more confusing question here, just describing how those lengths X are distributed. Next thing we're going to do is sketch the graph. Any questions at the moment? Okay, couple ways to sketch this graph. You're totally fine to just do this by hand. So if you wrote down something that looks like this, that's perfect as far as I could say. I mean, it's not perfect really. I'm not an artist. This is not a fully symmetric curve as it should be. But as long as you don't do something like, say, Let me try again. If you do a by hand sketch that goes like this is about the only time we could run into some problems because the related concept is this curve has to always be above the x-axis. So this is the major thing we're trying to avoid. Also, when you're trying to hand sketch these, make sure you're not doing something like this, for example. Problem with this curve is the curve never turns up unless it's going in the left or right direction and going towards this peak. So this would be totally prohibited. It has to be doing something more like that instead. So your by hand sketches don't have to be perfect at all. Anything roughly like what we have up here would do just fine. And if you look at that graph really carefully, there isn't even an x-axis. You have to imagine it. It's at this height by the red dot. It's not the black line at the very bottom. But this is another route to go. If you want, you can just use this graphic right here. Third way, you could type that into Desmos very, very carefully. That would work as well. But let's go with the route of just producing a graphic through RStudio, just in case folks would like to try that as well. So if you want to use RStudio to make the graphing happen, that's the purpose of all of this syntax right here. There's got to be a better way to say this, but this is how I implemented the normal curve. Take all of this, just copy it in. I did say before, you never want to type your syntax in Microsoft Word, but this is syntax that came from RStudio. It was pasted in, and that symbol right here by the red dot is correct. But if I try to type it here, that quote symbol is incorrect. Really hard to spot the difference. RStudio interprets this one differently than that one, majorly annoying. So my advice is never write syntax in Microsoft Word. But the syntax I paste in does have the right symbols. You can copy it out. So this is going to give us a plot. Just copy the whole entire thing. And let's come up here where we're going to drop the graphic. RStudio just needs us to drop it into this location here. And the way I've described this is, first, you have to make some changes. So this is the user interactive part. Then the rest of it just obtains the plot. So we just changed the first two things. If we leave it like this, and hit Control A, Control Enter, then that's the standard normal distribution. It's centered at 0. Its standard deviation is exactly 1. But we have to modify our parameters because of these values here and here. Oh, I just noticed the chat. Hayes says, I was having so many errors in RStudio with my first homework because of that symbol. Yeah, I hear you. That's really very frustrating with RStudio. Sorry about that frustration there. I think what Hayes was referring to is the issues with just quotes and stuff causing big problems. Well, in this situation here, we said, oh, the mean mu should be 54.00. I don't have to way of putting in a Greek symbol here. Maybe there is a way, but I didn't bother with it. I just sounded it out. Mu and sig for sigma. So modify mu to 54. I don't know if the 0.0 makes it. I know it doesn't make any difference. It just feels accurate. Put in 4.5 for sigma, referring to this value. Now, if we run this, it's exactly the same looking. But you know what did change? What happened was the vertical scale and the horizontal scale adjusted as we did this so that the curve always looks about the same. We hit on export, copy to clipboard. You could resize this if you like, but I wouldn't worry too much about it. Anything about like this is going to be just fine. In fact, when you do a hand sketch for the normal curve, most of often people don't even put in the y-axis. The y-axis changes in pretty unpredictable ways depending on the standard deviation. Let's take a screenshot here. And this would qualify for full credit if you do it this way, or just as another reminder, on the homework assignment, if this comes up, a by hand sketch is full credit as well. So I'm not too worried about doing perfect computer graphics on the normal curve. We only did it right here because it was convenient to do so, no other reason. So that's our distribution. The center of this distribution should be exactly at 54. So that would be right about here. Here's mu, and that would correspond to the main peak right up here. Then the way the standard deviation comes into the picture is this 4.5 would be a distance roughly about here. Let's check this out. If we took our mean, which was 54, add a standard deviation, 4.5, we get it to about 58.5, not quite there. But the way I eyeballed this was, think way back into Calculus 1 again about inflection points. The inflection point on this curve is where it changes from concave down, that's where we're at here. Over here, we're concave up. What I mean about that is you put tangent lines on this curve. Here's one tangent line. Here's another tangent line. It's not the most perfect tangent line, but there it is. Over here, the curve is below our tangent lines, so it's concave down. Over here, the curve is above tangent lines, so it's concave up. Somewhere in here is a transition point. Anyone recall what that was called? No worries if you're a little rusty on it, I totally understand. It's called the inflection point. So where it transitions from concave up to down, this inflection point somewhere in there. So that's why I felt this distance should get us to sigma. So that's one way to think about the plot and how it relates to the parameters. But we have other things we want to do this plot. We need to describe how in the world do we do probabilities off of this graph? What is this even describing? We'll come back here. It was describing x. So there's an axis going this way. Let me draw it in just for the emphasis. Here's x. And what was x? That's easy to forget. It was the length of the randomly selected fish from this population, meaning these herring. I'll just say this population, but let the context carry it. So x is the length in millimeters of a fish in this population. I'll use pop shorthand for population. We said the center, the mean is at 54 millimeters, so right about here. And now the interesting questions we can now attach to this is this statement right here. The probability that a randomly selected fish from this population has a length that's less than 50 millimeters is described this way. We call back the variable x, which is the length of the fish from this population. Might as well convey it this way. When we say it has a length less than 50 millimeters, that's this portion of the probability statement. And by the way, whenever you see something that says probability statement, we're referring to this. Let me use an arrow. This is the probability. Statement. So reading this out, we would say P. Well, we would really say the probability of where P is. So it's the probability that a randomly selected fish from this population is less than 50 millimeters is 0.1870. You could convert this to a percentage if you prefer. No difference there. It's just a unit change. And if you went with the percentage, you would say, well, 18.70% of the fish from this population is less than 50 millimeters in length. Or you could say, if you select one randomly fish from this population, 18.70% chance it's less than 50 millimeters. So that's what the probability is saying. But up here, here's what it's doing. We go to this inequality, less than 50. Here's our x-axis. Because of the less than direction, we're taking all of this area that's being highlighted in this way. And this right here is, as an area, equals probability x less than 50. So in this model for probabilities are areas under the curve. And it's in that sense that there is a bit of a Calculus 1 prerequisite to this. except that we are not integrating the probability density function of x. That is a tough integral. We're just using approximation integration methods through RStudio to get this area. Imagine you're just doing the midpoint rule with n equals 1,000. It would take a while, but RStudio doesn't care. It does it very, very fast. So that's what this probability statement is saying. And what it says now is this area is equal to 0.1870. So all that area there is exactly that figure. Well, to 4 decimal places of accuracy at least. Well, again, just a write-up of this. That means there's an 18.70% chance of selecting a fish from this population with length less than 50 millimeters. And, well, we did this portion. I should have read that first. Sorry, that's kind of out of order. We were meant to shade the portion of the graph here that corresponds to the given probability. Sometimes this is a pretty common question in Chapter 11 as a concept question, just so that we are thinking about what in the world did RStudio do when we go to make it compute a probability. It's good to have a picture in the back of your mind because it informs if you made any mistakes, if the probabilities are reasonable, and even how to set it up in RStudio in the first place. Sometimes a picture is a great thing to have. Here's where it gets a little bit weird next on part D, but any questions first with part C? Okay, now that we're dealing with probabilities, we should mention there's a couple kind of models. The model that we're using is the continuous probability model, where we can take a continuous function, the probability density curve, and probabilities are areas. There's other models where you're dealing with a discrete sample set space, but this one is all about areas. And it has some interesting defects. If we ever ask a question, what is the probability that x is 50 millimeters? It feels like we should have a decent answer for that, right? Except the answer is no, it's always 0. Doesn't matter if you said 50 millimeters, 51 millimeters, 20 millimeters, the answer is always 0 to this. Whereas this one had a non-zero answer. Anyone spot what's going on with this probability statement here? Yeah, go ahead. Not included it by, sorry, my bad. I think you're on the right track. The trouble here is that this one did exclude the 50, like you're saying. And notice how I drew the line. I drew it as if I did include 50. Does it matter? That's a really good question because we are integrating and getting areas. So again, from a calculus 1 take on this area of 0.1870 is a definite integral. Well, it's improper type 1 because the lower bound goes negative infinity because of the less than direction here, but it goes all the way up to 50. So this part copies in from right here. But notice when you do this integration problem in calculus 1, there's no way to signify the difference between less than and less than or equals. It's impossible. Either way you say this, you're putting 50 up here on the upper limit of integration. Very, very strange. But that's because the definite integral is measuring areas. And whether or not you include one vertical strip turns out is meaningless. Make that a dashed line to say you left it out. It does not affect the area because the area cannot be affected by a single line. Its area is 0, for example. No change whatsoever. So whether you put less than here or less than or equals, this is really very weird, it will give you this same exact value. You might have noticed in a TID4, if you've ever done normal problems there is no way to tell the difference between a less than or less than equals. And same in RStudio, nothing here is going to help us make that determination, but it's because it actually doesn't matter. They're full on equal. So for the explanation on this one, we can say probability x equals 50 equals 0 because probability x equals 50 is really, when we really investigate the model, an integral problem. It'd be integrating from, well, 50 to 50, because there is no range here. It's just one point that we're dealing with. If you integrate from 50 to 50 on any curve, doesn't matter how much calculus you've taken, this is automatically zero. The moment you find an antiderivative, you take it at 50 minus the antiderivative at 50 again, just zero any way you look at this. So I think this is a great way to say it because it's tying together calculus. That's not the required way you can say this. There's other ways to describe it. You could just say probability x equals 50 is zero because the area of a vertical line is zero. That would be a vertical line that's dashed right here as we settled it. So again, really strange defects with this probability model, yet it's super useful. We just have to know how to ask the right questions. Every question has to be an interval. It could be less than 50, it can be between 50 and 45, anything like that. But if you say this, it's automatically probability zero. Massive frustration because if that's the thing you're trying to answer, you've got the wrong probability model. It can't do it for you. And here's the other side effect between all this. Because the probability x equals 50 is zero, we have this inequality. It turns out it makes literally no difference in this probability model. If you formulate your problem as x less than 50, here we would say probability the randomly selected fish is strictly less than 50 millimeters. Or if you said the randomly selected fish is less than or equal to 50 millimeters, no effect. Probability is the same because of what's going on here. It's said to explain why, so you could say all that in wording, but another way to think about this is probability x less than or equal to 50. There's a different way to say that. That's a less than or equals. So inside the probability set function, you would say probability x less 50 or x equals 50. Then these are completely disjoint sets. That means across the OR operator, other books on probability would put a union symbol instead of the OR. Ours uses ORs. But across either a union or an OR, you have an addition formula that says that this is probability x less 50 plus, coming from the OR, probability x equals 50. And from the last statement here, that's just a zero. So we get probability x less than 50. So those are the kinds of things I want to get out right away before we go in RStudio and do any computations. The normal probability model has a lot of weird side effects only because probabilities are areas, and we're getting those areas through the definite integral right here. Well, any last questions, folks, about those strange oddities? Okay, well, let's calculate something before we get too far, just because we're kind of running out of time. We're not going to try to finish these notes today. But before we do anything at all, I'd say it's a good idea to show just how this goes. We're going to do a whole lot on these notes, starting on this problem down here. But while we're looking at this one, let's compute this probability 0.1870 through RStudio. Here's how it would go. Let me just reconfigure my windows here. It's always kind of struggle to get everything to fit just right. For this, I'm just going to do a computation. Think of me using this as just a calculator, like a TI-84. I'm not worried about building a script. To do this probability, we start by just typing out P, because we want a probability. Then we go to X. X is normally distributed, so we say P norm. So we're going to get probabilities from the normal distribution. Open a parentheses to throw in a function. And first thing we put in is this value here from inside the probability statement, 50. And notice the other parts of the input. We need a parameter for the mean and the standard deviation. Let's see where we set all that. put these in, 54, 4.5, and then we have to pick a directionality as well because this says shade to the left to get your area. But the good news in this problem here is RStudio automatically assumes you're going to take the area going to the left. So hit enter on there, and I have some massive failures here. It's because my graphics are all messed up. Sorry about this. Okay, that should work. Hit enter on that statement, and that's where the number 0.1870 came from. Again, we're going to look into this in high detail, but I'll take a screenshot here just for the sake of the notes on how we checked that. Then, by the way, what would be the area of this region right here? Well, the total area is exactly 1, right? So all you would do is get the area here by the red dot, 1, let me do it this way. Take this, and then 1 minus. So I hit up arrow to call back this thing, which is just a fast way to put in 0.1870. So 1 minus p norm gives you this area. And yeah, that figure looks about right, 0.1829686. So if you ever have to get the area to the right, because there's a greater than sign there, that's how we would do it. Or RStudio has options here. Hit up arrow twice. If you didn't want this area, because there's a greater than sign here, and you want this area, put in another statement. Go lower dot tail equals false. It's always defaulting to true, so now I've controlled it to get this area. It should be exactly that figure there. Let's take a look. And yeah, we're in business. So for the folks that have taken probability, area to the right here could either be through the complement rule, which is what this is, or it could just be by controlling one of the parameters in the normal function. Usually I go this route. I feel like even though the syntax is a little bit longer, it feels like it is just better understood going in this way. So that's how to do some really fast normal computations just through the p-norm function. We have a lot more to say about it. There's also the q-norm function that's going to come up. But that is a way to do it. Let me put it down here. At this stage, I do have a question for the class. We're using RStudio a lot, mainly for inferential statistics, but there could be other ways to get that computation. First, Ben says, I missed what F was. Oh, sorry about that. F here is just a quick way to say false. And you know, I think the better way to do this is literally write out false that way, because that's a little bit safer in the syntax. I think that's a good statement right there. If you put in F, then RStudio is going to immediately assume that that's a Boolean and consider it false. But there are times where that can cause problems in the code, so it's probably better to just go all caps false that way to get the same result. When I put F there, I'm just being kind of lazy with that. But does that make sense there, Ben? Yep, absolutely. Other questions so far? Okay, then the other question I had for the class is there anyone in class here today that uses, say, a TI-84 to do these computations that would like to see this redone? Okay, great. Thanks for asking about that. I'm sure there's probably other people as well. Because again, if you have taken statistics before, you've probably learned all of this stuff once already. And I'm asking you to relearn it by pulling out RStudio. My emphasis is you don't have to relearn a way to do this if you prefer to do it a different way. So here's how we go. We go to your favorite calculator, whichever one it might be. I'll use the TI-84. We want to get this value out. Hit second bars. They'll put up a list of distributions, and we want normal CDF. The PDF stands for probability density function, so you'd only use that if you want a point on the graph. That's not useful to us. CDF stands for cumulative distribution function, which means you're starting at a point and accumulating the area going either to the left or to the right. So this one does it for us. Hit enter there. And it's a little tricky because we need a lower bound, but we have none. X is taking on all values going to the left forever, which means it takes on negative values as well, but it's not so concerning because the curve gets so close to the x-axis by the time we're at 35, those negative values have little contribution, if any, to the probability. But still, to get an answer as accurate as possible, go -10 power 99, and that's the best way to approximate a negative infinity on a finite machine like this. I mean, even RStudio has to do this. It's doing an approximate integration, and it's a finite machine just as well. For the upper bound, you pull in this figure, 50. For mu and sigma, you go back to the model, 54, and 4.5. Then hit enter a bunch of times, and you get this figure to come out, 0.1870. So just as before. So anytime we do a normal probability computation, for anyone at all that would like to see it done in a different way, I'm very happy to pull it up. Just takes a moment. Any questions at all, folks, through the TID4, getting that figure? Okay, well, let's go on to the next part of the notes. Oh, I got a chat first. He says I got 1 on the calculator. You know, that's a possibility that if you've got a 1 on that, it could be something to do with, let's go to normal CDF. Possibly the difference between lower and upper could be the thing, or I would suspect it might be something to do with the parameter. It should be exactly 4.5, 54.0. So just as a quick screenshot, it should look about like this before you hit enter. Is there anything there that needed to be changed or helped out? Gotcha. So for the upper bound, yeah, if we put in, say, maybe a 10 power 99, let's actually do that because it's an important concept of the normal distribution as well. If we do this, now it doesn't even matter what parameter values you take. It's going back to this concept. The area under the curve is mysteriously exactly 1. Integration in Calculus 2 explains this in a great detail. But hit enter on all that, and that's this matching up with that statement there. Area is exactly 1, and we integrated from negative infinity to positive infinity. Well, the best we could do with the finite machine. Other questions at the moment so far? Okay, well, next thing we want to take a look at, now that we're dealing with normal distributions, is knowing when we can use it. This is a pretty small concept because we talked about it before. Also above here, just in case you're curious, there's a little information on how it connects with standard deviations. It tells us about how much area is in a particular region organized by standard deviations. But this is really just here for the sake of completeness, just another look at the normal curve. We won't be using this rule directly. We'll be using either a TID4 or RStudio to get exact areas. Then beyond that, other part of the notes is us just determining if it's reasonable to use a normal curve or not based on the histograms. Again, we talked about these before, so the short of it is what we're looking for is something that is at least roughly symmetric. This has some pretty decent symmetry. This would be, I'd say, highly symmetric on this. And if we tune the parameters just right, we would probably use a sample mean and call it a parameter, the sample standard deviation, and use that as its parameter. We might find the curve would look about like this when we superimpose it over the histogram. Again, it's not perfect, but it's us trying to model the data. We're not expecting perfection. And it's sample data in the first place. It's not like we're putting the whole population into a histogram. So there's lots of ways that this model is going to fail. It fails really bad on data that looks like this. We saw this in the chapter 2 notes as well. If you try to fit a model like we did up here, the peaks have to line up. So if you're trying to line up the peaks on these data, it would look about like this. And it's doing a terrible job because there is no area corresponding to about half the curve. We'll probably make it look a little bit better, but still here, this is a really bad situation. So on the one above, we could say, yes, it is reasonable to use that normal distribution since these data are symmetric. And it would still qualify even if it deviated from symmetry even a little bit more. Until we decide it's skewed, then we've got a big problem. So down here, we'd say, no, it is not reasonable to use that normal distribution. Because the data is skewed. And you know, that feels really unfortunate at first because a lot of populations we need to study very carefully are just naturally skewed. Means we can't use a normal distribution, and that would mean the course is practically over because we can't do any inferential statistics at that point. Except that's not really true. The reason statistics is so concerned about this distribution right here is not because we can sometimes model it to sample data like we were just looking at. It's because this is the right probability distribution for modeling a sample mean. A sample mean does follow this distribution better and better in the limit as the sample size n gets higher and higher. So even with data that looks really, really bad in the population, say this is your whole population and it's a terribly skewed set of data, if our sample size is large enough, the normal model still enters the picture, not for these data, but for the sample's mean. And that's our hook into inferential statistics. The normal distribution is more about the sample mean being distributed than it is about these populations. But nonetheless, if we are introducing the normal distribution, we should still practice it. So here's some routine problems where we're not doing any inference, we're just practicing using the normal model. Any questions first at all, folks, with these graphs here? Okay, so here's our next problems. Here, we're going to be doing these top to bottom, using RStudio, sharing the syntax, and show how it goes in an RStudio environment. And again, for any of these problems, if you want to see it redone with the TI-84, don't hesitate to ask. Very happy to show the dual computations. So this is a pretty fun problem from, let's see, 1993, so it's a little bit old, a few decades, not too bad. It's about the time it takes a driver to react to the brake lights on a deaccelerating vehicle, and they say that's critical to avoiding rear-end collisions. I guess that's true, I would agree with that. But this at least tells us what the context is all about. They did an experiment where they built out a little system to imagine you're in driver's ed, you're in something that looks like you're driving a car. They had something in front of you that would model a brake light, and all these people had to do was respond to the brake signal in front of them. We're trying to model what normal traffic would be like if you're driving for real and someone hits their brake light and they're immediately in front of you. How long does it take you to react? That's a pretty important figure. And so that's what they did in this article right here in Ergonomics. That's kind of a weird journal, but that's what they did in that journal. It suggested that the reaction time for an in-traffic response to a brake signal from standard brake lights can be modeled with a normal distribution. So that's our hook. We can use the normal model now. The mean is 125 seconds. And this is based off data from the article. So you could call this X bar, except that if we're about to model with a normal distribution, we're treating that as a parameter. It's describing the whole population through this model here. So we'll say, even though it's not true, it may not even be a great approximation, it's the best thing we have to fit the data. The mean, mu, is 1.25 seconds. And standard deviation, sigma, is 0.46 seconds. So that's the whole model. This is just as important. Anytime we write down X, think of the context of X is just time in seconds to respond to that break signal. We want to know right away what's the probability distribution of X, but we could say X is distributed normally because they told us so and we're going to trust it. You don't have to buy the article to see if it's reliable. So it's distributed normally, having mean 1.25. You could put units here if it helps out, but usually I would suppress the units if I'm using this kind of notation. So 1.25 goes here, and standard deviation 0.46 goes here. Again, if you got in the habit of putting the variance in there, you don't have to change. Everyone would know you threw in the variance instead of the standard deviation. That would be totally fine. But that's our probability distribution, this statement right here. Following the color coding is just conveying all this stuff that was said in the problem. Then from here, we're ready to start calculating probability values. We want to find the area under the curve between 1 second, 1.75 seconds. And this is our tougher part. Then after, give a practical interpretation. We might have to come back to that because of our time constraint. Let's go for at least one probability computation. So to do this as fast as possible in RStudio, I think a good workflow is always just define the parameters first and actually use the script on this one. It's pretty reliable, especially if you have multiple parts. You want to just reuse what you've got. So phonetically, I'll just say the Greek letter mu is mu, 1.25. Sig, that's kind of concerning. I don't know if this is the best choice because if I type sig, RStudio has some things there. So I haven't gotten in trouble with that just yet. I'm going to continue to use that, but if that worries you, you might want a different value than just sig. But sig stands for sigma, 0.46. Now next, we want to do this computation here. Well, it's asking for the probability that X is between two different values. And the way we implement that is we go p-norm. We take the upper value first, 1.75. We have to say what the parameters are when we use p-norm, but we just call back mu sigma. But this isn't the right answer because if I type just this much, I'm interpreting the problem like this, probability that X is just strictly less than 1.75. So we need a little bit more that goes in here. Let me fix the notes first. To get the fact that X is bounded between the two, we go minus. And let me see if I can put this over here. There we go. We go minus. P-norm function just comes up again and use the lower bound. 1.00, type in mu sigma, comma separated. Then if I hit enter on this, well, not really hitting enter, if I hit Control A, Control Enter, this is the value that we're going for. So the probability is 0.5681 upon rounding. Usually 4 decimal places is pretty good generic advice for a probability. So let's say from here, probability 1.00 less X less 1.75. That's 4 digits, but that's a lot to remember for me right now. 0.5681 is the value that we would get. And that's the syntax that implements it for, well, at least part A. We're going to build on this when we come back to the notes. But if you want to get started on doing some of these problems, here's the syntax that we've used so far. Where's my outer box? There it is. So that's a way to do it. And if you're a TI-84 fan, there's a fast way to implement this as well. Hey says, oh, let me see, p-norm 1.5 mu sigma minus p-norm 1 mu sigma, and you've got a very low value. It might have to do with what you've stored as your mu and sigma. I would double check these values right here just to see if maybe mu could be off or potentially sigma. Does those two look accurate there? And by the way, one thing that you could do, which everyone in this class is welcome to do, is if I hit Windows Shift S and snip this, you can actually just throw that right into the chat right here, which could be popped out. supposed to be able to be popped out. With that button, oh, I have to save it. Well, that's a way to pass files. I guess it's more complicated than I hoped. But does that help out with the two issues here and here? Getting the value 0.5681? Awesome, glad to hear that. And last thing, if you're doing in this calculator, those second bars, normal CDF, all you have to do here is say your lower is 1.00, your upper is 1.75. Of course, give it the right parameter values for sure, and that implements this. Kind of weird, RStudio is more complicated than the TI-84 with their syntax because of the way it does not handle a lower and upper simultaneously. Well, this is a good stopping point for us though. Any questions at all, folks, to this stage? Okay, we didn't get too far to this portion, so this is a reminder for me. We'll make sure to hit the practical interpretation because this would be the related concept question again as an exam problem. I can't ask you to do this in an exam setting because we're not necessarily strictly teaching the calculator and we're not bringing RStudio. I would give you a probability like this and then it's your job to say what it means right after. Sometimes that's pretty tricky, but we'll practice that next week. Have a great weekend, folks. I'll see you all on next Tuesday.
Thank you.
Yep, take care.
My sign, I apologize for.
Awesome.
Bring it. I printed it out and, I must have dropped it.
Oh, gotcha. Yeah, no worries.
So I just, quickly sent the PDF to you.
That's perfect.
PDF, but Word.
You know what? That's even better for me since I take the PDFs and convert them back to Word in the first place anyway. So that's terrific. Thank you.
Have an excellent weekend.
Thanks, you too. Any questions?
Yep. So, it's you that I'm curious, first one doing that. I'm curious how you condensed it. So for number 3 right here.
Yeah.
I want to see if I did this right because you condensed it down, the final answer being 1/210.
Yeah, let's see here. So cosine 9, sine power 5, they're both odd, so either substitution is gonna work. Sine x is a good choice, but you know, if you go sine x, the trouble is you have cosine power 8, which is pretty complicated. But let me see here. Do you use sine x? Do you use cosine x? To give away one cosine here, so now it's cosine power 8, which is, this is where it gets really pretty tough. The problem with that right there is, kind of cool just to be able to draw on the screen like this. One, or cosine power 8 of x would really be cosine squared of x to power 4, which turns into 1 minus sine squared x to power 4, which means you're dealing with a 1 minus u squared to the fourth power, and it gets pretty complicated. But because they're both odd, one thought on this one is pick your u to be the one with the higher power. Then this sign would drop down to sine power 4. Sine power 4x is easier to handle because this becomes sine squared x squared, which is 1 minus cosine x, cosine squared x squared, which turns into 1 minus u squared squared. But I mean, it's still some algebra here, but nothing like that one. That one's way worse to navigate through.
Okay.
So there's just a tiny mistake there. It really turns into that, which is tremendously awful. But I would encourage you to try u is cosine x on this one to simplify the work.
And then this one, we didn't have an answer for from the whole, which is even problem, so I just wanted to see if I went through.
Oh, right, yeah. So these are annoying because a small chain rule comes up with t over 2.
Oh, does it?
Yeah, it means when you go for a u equals sine x, we've got to go u equals, let's see, cosine's odd, so we definitely pick sine like you did. But u has to be sine of, I'd write it this way, just out of safety, 1/2 t. Then differential du would turn into 1/2 cosine 1/2 t dt, where that 1/2 right here is through the chain rule now.
Okay, and then solve it through that instead of plugging in what I did.
Yeah, this is a pretty good answer, but it only had that small issue there to there. The rest of the approach with sine to cosine means you give up a cosine, so that looks good, u squared, and that would look good. So yeah, that's accurate right here. You're on the right
So
track.
right here, it's okay, but then when I plug it in, I have to plug it in with those different. or
Yeah.
Actually, because d of u, I would have to pull out a 1/2, huh?
Yeah, the 1/2 also enters into the picture as well. So you have a really great answer. There's just a couple of those small little things.
Okay, and then, I can't find, trigonometric identity to plug in for this one.
For that one, when you go to the thing that had the 3 strategies for sine and cosine powers, there's another identity that goes like this. One for sine squared, one for cosine squared. These are referred to as the reduction formulas, and they both go 1/2 of something times. The sine version is 1 minus, cosine squared version, your problem is a 1 plus, and it's a cosine 2x here, cosine 2x here as well. So we use these two so-called reduction formulas whenever that kind of situation comes up.
So I'm like, 1, 2, 3,
Sounds good. Awesome. Oh,